Andreas. Hello, everybody. Thank you for your participation to this third seminar. The presentation of today is given by Dr. Chaima Zammali. Chaima has defended her PhD thesis recently at Sorbonne University in Paris. And the presentation of today deals with robust state estimation for switched systems with an application to fault detection. So Chaima, you have about 40 minutes to present the work, and after we can ask some questions.
Okay, thank you, Mr. Raisi, for this introduction. Hello, everyone. To begin, it is also my pleasure to participate to the International Online Seminar on Interval Methods in Control Engineering. So today, my talk is about robust state estimation for switched systems, application to fault detection. We are interested in the context of this project in switched systems, which represent a special class of complex systems. They are composed of a finite number of continuous subsystems, named generally modes, and a logical rule that operates switching between subsystems. The main interest of studying switched systems is justified by their hybrid dynamics, continuous and discrete, and their ability to represent and control a wide range of industrial systems in many engineering fields, such as opening and closing power switches, biological cells duplication and division, aircraft moving safety through the airspace system, and many other examples. Over the last years, switched systems have been widely studied in the frame of state control, state stability, state estimation, and fault diagnosis. In the context of this project, we are interested in state estimation and fault detection for switched systems. In fact, in most practical cases, the entire state cannot be completely measurable. This is due to technical or economic reasons, like the high cost of sensors or their insufficient precision. So the implementation of a state estimation algorithm is needed in order to reconstruct the internal state vector from the input and output measurements. This step, the state estimation step, it is primordial in order to deal with fault detection for switched systems. Let us begin with the state estimation topic. So a number of results are available for the estimation problem using Luenberger observers, Kalman filter, sliding mode observers. Other observers like adaptive in known input high gain observers are also investigated in order to solve the estimation problem. Most of the existing results focus on point estimation, which in some cases cannot converge to the real state due to the presence of uncertainties. To handle this problem, interval observers are considered as an alternative by computing the set of admissible values and providing the lower and upper bounds of the state vector. In the literature, interval estimation has been introduced for biological systems in the work of Gouze, and then applied for different classes of systems, such as the linear time invariant systems, linear time varying, linear parameter varying, and nonlinear systems. Interval estimation has been also considered in the case of continuous time as well as discrete time switched systems. Actually, most of the existing results on interval estimation for switched systems are developed in linear time invariant settings. That's why the main challenge of this project is to propose a new interval observer for a class of linear parameter varying switched systems subject to unknown but bounded disturbances and using a polytopic formulation. The main advantage of using the LPV formulation is that it provides an elegant way to deal with nonlinear systems. So as mentioned before, the state estimation is primordial in order to deal with fault detection. And as well as interval state estimation, interval observers have been also proven to be effective in fault detection. In fact, they can deal with large uncertainties, and they can provide a systematic way for residual evaluation without designing residual evaluation functions and threshold generators. In the literature, interval observers have been considered for certain linear systems, nonlinear systems, linear parameter varying, and more recently for switched systems in order to deal with fault detection. However, most of or some existing works cannot provide accurate fault detection results since the effect of uncertainties is not minimized. That's why one of the essential requirements is to consider robustness against uncertainties. Robustness can be analyzed using the H-infinity performances. In fact, the H-infinity norm is a measurement of energy to energy gain, which require that the uncertainties should be energy bounded. However, from a practical point of view, some signals cannot be considered always energy bounded, but have instead bounded peak values. Therefore, it is more reasonable to use the L-infinity performances, which describe the peak-to-peak performance index. In the context of this project, we aim to propose an interval method to detect tensor faults for a class of discrete-time switched systems using the L-infinity formalism. On the other hand, interval methods are based on positive system theory, which requires that the error system is simultaneously cooperative and stable, which is a restrictive and conservative assumption. That's why some authors propose a coordinate transformation to relax the cooperativity constraint. However, it is still hard to merge the coordinate transformation with some performance constraint. So in view of this major problem, Zonotopic and ellipsoidal analysis are developed in order to provide accurate fault detection results without considering the cooperativity assumption. To the best of our knowledge, Zonotopic and ellipsoidal analysis for switched systems in order to deal with fault detection have not been fully considered in the literature. That's why the first contribution is based on a novel robust fault detection method using a novel point assignment technique, which is used to improve fault sensitivity and where the residual evaluation is based on the Zonotopic method. In the second contribution, a robust fault detection method is considered using L-infinity performances with ellipsoidal analysis. So after introducing the context of this presentation, we are going to give some results about interval estimation in the case of synchronous switched systems, and then set membership fault detection frameworks for switched systems will be presented using interval, zonotopic, and ellipsoidal analysis. And finally, we give a conclusion. We begin by the interval estimation in the case of synchronous switched systems. And we consider the following linear time invariant system. The matrix A is the state matrix, phi is the input function, and C is the output matrix. For this system, we assume that there exist two known functions, overline and underline phi, such that phi is between two bounds. We suppose that the initial state x0 satisfies the following inclusion. We assume also that there exists again L such that A minus LC is sure stable and non-negative. And finally, the pair AC is supposed to be detectable. Under these assumptions, the goal is to estimate two states, an upper state, which is noted by overline X, and a lower one, which is noted by underline X, satisfying the following inclusion. The interval observer structure, which is proposed by several authors in the literature when considering a linear time invariant system, is given by this set of equations, where L is the observer gain to be designed to satisfy two conditions. The first condition is the cooperativity property, which means that the state between two bounds. And the second condition is the stability of the upper and lower bounds of the estimation errors. We begin by the cooperativity property. Here we have the definition of a cooperative system. So if A is a non-negative matrix, x0 is higher or equal to 0, uk is higher or equal to 0, so we can say that this system is cooperative or non-negative. According to this definition, the goal is to prove the cooperativity of the upper and lower estimation errors. So we have by assumption the gain L is chosen such that A minus LC is non-negative. By construction, we can prove that the initial conditions of the estimation errors are higher or equal to 0. And these expressions, which are equivalent to the input vector, like UK, are higher or equal to 0 since the input function is bounded. In addition to the cooperativity property, the convergence of the upper and lower estimation errors should be also satisfied. By assumption, we have A minus LC is sure stable. And the boundness of the function phi implies the boundness of these expressions. So the cooperativity and the stability conditions become more complicated when considering a linear parameter varying system. That's why in the context of this project, we aim to relax or the cooperativity and the stability conditions will be relaxed. We consider in this presentation the following discrete time LPV switched system, where W sigma is the state disturbance, V is the measurement noise, eta sigma is the collection of measured time varying parameters, and we denote by sigma the index of the active subsystem, which is supposed to be known. For ease of notation, we will use Q as the index of the active subsystem. Some assumptions are required to design the interval observer. First, AQ, BQ depend oftenly on eta Q. We assume that the initial state x0 satisfies x0 between two bounds. The measurement noise and the state disturbances are unknown but bounded, and eta Q are constrained in polytopes which are noted by EQ, and we denote by eta QI the verses of each polytope. And finally, for all the verses, the pairs AQ, eta QIC are detectable. Under these assumptions, the goal is to design an interval observer for the class of discrete time linear parameter varying switched system using a polytopic formulation. To that end, the proposed interval observer structure is given by this set of equations, where LQ are the observer gains to be designed to satisfy the cooperativity and the stability conditions. We begin by the cooperativity property, and we define to that end the upper and lower estimation errors of a line and a line X. Using these expressions, the dynamics of the estimation errors are given by this set of equations. And according to the definition of a non-negative system, the red matrices should be non-negative matrices. The initial conditions of the upper and lower estimation errors should be higher or equal to 0, and the blue expressions should be higher or equal to 0. According to ETEL, if AQ and LQ depend oftenly on eta Q, so they can be written as a convex combination, such that AQ eta Q is equal to the sum over I of lambda I AQ eta QI, where these matrices are the verses of the state matrices of each polytope. Also, the same thing for LQ eta Q, it is equal to the sum over I, L lambda I, LQ eta QI, where these matrices are the verses of the observer gain of each polytope. According to the convex form, the error dynamics can be expressed on the vertices of each polytope. So these matrices are non-negative is reduced to prove that these matrices are non-negative on their vertices. In addition, we have overline X is higher or equal to 0 since the state disturbance and the measurement noise are supposed to be unknown but bounded. By construction, we can prove that the state is upper bounded, and same arguments could be used to prove that the state is lower bounded. And thus, this inclusion is satisfied. The state is between two bounds. So, apart from the cooperativity assumption, which is relaxed thanks to the polytopic shape of the time-varying parameters and expressed on the verses of each polytope, the stability also of the proposed observer should be also satisfied. To that end, we begin by the definition of the stability analysis, which is the property of a system to return to its equilibrium point after it has been deviated from its initial position. In the presence of unknown but bounded disturbances and noises, the input to state stability could be introduced. In fact, it provides a framework about stability with respect to input perturbations. It means that a system should be bounded if bounded inputs are injected and should converge to equilibrium when inputs tend to 0. This lemma is a very common lemma in the literature when considering multiple quadratic Lyapunov function and average dwell-time switching signal. We will prove that based on the red inequality, the stability of each subsystem will be satisfied, and based on the blue inequality, the stability at the switching instance will be also ensured. In this part of my talk, we are interested in checking the stability of the upper estimation errors, and the same arguments could be used to prove the stability of the lower estimation errors. So the stability of each subsystem is reduced to the feasibility of the following linear matrix inequality. We can see that these LMI have to be checked only on the verses of each polytope in order to avoid any infinite dimensional problem due to the time varying parameters. Concerning the stability at the switching instance, it is based or it is reduced on the feasibility of the following linear matrix inequality, which is deduced from the blue inequality, which is in the previous lemma. In addition, it can be also easily shown that the upper estimation error is bounded by this expression, which should be made as small as possible in order to enhance the performance of the proposed observer. So minimizing this expression is reduced to minimize the value of gamma. Okay, so in addition to minimizing the value of gamma, we aim to minimize the value of mu in order to look for an optimum dwell time. And thus the optimum the following objective function. As I said before, same arguments could be used to prove the boundness of the lower estimation error. So in the simulation study, a discrete time LPV switched system is defined with 3 subsystems. The state initial conditions, the measurement time varying parameters, the state disturbance, and the measurement noise are supposed to be unknown but bounded. And the parameters alpha, alpha 1 are chosen to solve the optimization problem. the Lyapunov matrices and the observer gains are given by these values, we get mu is equal to 2, which gives an optimum dwell time higher than 0.301, and we get gamma is equal to 2.12, which gives an optimum interval width. So the simulation results are depicted in these figures. The first figure shows the evolution of the switching signal. It indicates the active subsystem. From the second and third figure, we can see that the state is between two bounds. And from the last one, we can see that the upper and lower estimation errors are always positive and bounded, which illustrates the efficiency of the proposed interval estimation in the case of synchronous switched system. So after giving some results about interval estimation for the case of synchronous switched system, we are going to present set membership fault detection frameworks for the same class of systems, which is this class of switched systems using interval, Zonotopic, and ellipsoidal analysis. We begin by the interval-based fault detection method, and we consider the following discrete-time switched system. The matrices AQ, PQ, DQ, even with appropriate dimensions. And for this system, we assume that the measurement noise and the state disturbance are unknown but bounded. We suppose that the initial state satisfies this inclusion. The initial state is between two bounds. And we suppose that the pairs AQC are detectable. Under these assumptions, the fault detection interval observer is proposed as follows, where overline and underline Xi are intermediate variables, overline underline X, overline underline Y, and R are respectively the estimated upper and lower bounds of the state, the output, and the residual signal. Overline underline delta are bounded expressions since they depend on the boundness of the state disturbance and the measurement noise. We denote by overline underline LQ the observer gains to be designed. And we have these matrices are supposed to be constant and should be designed to satisfy these conditions. It is worth noting if TQ is equal to the identity matrix, NQ is equal to the zero matrix, so the proposed interval observer is equivalent to the classical interval 1. And in the case of classical interval observers, the gain LQ should be designed such that these matrices are non-negative, which is a restrictive and conservative assumption. So by introducing the weighted matrices TQ and NQ, the proposed fault detection observer can reduce the conservatism of gain matrices and can provide more design degree of freedom. So using the proposed interval observer, which is based on the TNL structure, the non-negativity, the stability, and robustness against uncertainties will be studied in next slides. We begin by the non-negativity property. In fault-free case, the relation X between two bounds is satisfied if these matrices are non-negative. In fact, when F is equal to 0, we have the estimation, the error system is equivalent to this set of equation. And according to the non-negative, the definition of a non-negative system, the red matrices should be non-negative. The blue expressions are higher or equal to 0. And by construction, the upper and lower estimation errors are higher or equal to 0. Thus, the state is between two bounds in fault-free case. In addition to the non-negativity property, The stability of the residual framers should be also satisfied. To that end, we propose a new augmented system, which is given by this equation, where an augmented state and an output are given by these vectors. So in order to facilitate the analysis of the error dynamics is split into subsystems. One is decoupled from the effect of the sensor fault, and the other one is only affected by the sensor fault. Based on this representation, the goal is to compute the fault detection observer gains such that the error system is stable and the residual signal satisfies the following L infinity performance. To achieve these 2 points, sufficient conditions are given in terms of linear matrix inequalities using multiple quadratic Lyapunov functions. So after designing the fault detection observer gains, the fault detection decision is based on determining whether the zero signal is excluded from the residual boundaries or not. In fact, in fault-free case, the output signal is consistent with the estimation of the proposed interval observer, so the zero signal is between 2 bounds. However, when in faulty case, an inconsistency on the output signal can be detected, and it indicates the existence of a fault. We can see from this figure, the fault-free case figure, that the zero signal is always between 2 bounds, an upper bound and a lower bound. However, in faulty case, when a fault occurs at this time instant, we can see that the zero signal is excluded from the residual boundaries. So to highlight the effectiveness of this method, we consider a discrete time switched system with 3 subsystems where the initial state conditions, the output and the state disturbance are supposed to be unknown but bounded. The stability analysis is based on multiple quadratic Lyapunov functions. So in the simulation study, the first figure shows the evolution of the switching signal, and the second figure shows the evolution of the fault which is supposed to occur between the time instant 13 and 50. So in fault-free case, we can see that the cooperativity assumption is ensured and the zero signal is between 2 bounds. When a fault occurs at the time instant 13, the fault can be detected at the time instant 31, and the zero signal is excluded from the residual boundaries. In the case of a small fault, we have performed a comparison between the TNL method and the classical interval observer. We can see that using the proposed TNL method, the zero signal is excluded from the residual boundaries, which are in dashed lines, when a fault occurs. However, when using classical interval observers, we can see that the zero signal is always between the upper and lower bounds, even after the occurrence of the fault. So we can say that the proposed interval-based fault detection method using the proposed TNL structure provide accurate fault detection results. And the implementation of this method is very simple and does not require any computational complexity. However, this approach is based on the non-negativity of these matrices. In view of this drawback, Zonotopic-based fault detection methods could be provided and could be developed to provide accurate fault detection results with relaxed design conditions. To that end, in this part of my talk, we are interested in designing a robust fault detection method using Zonotopic analysis. The proposed approach is robust against uncertainties based on H infinity criterion and sensitive to fault using a novel pole assignment technique. Before giving some details about this approach, we give the definition of NSO the Zonotope. So NSO the Zonotope is the affine image of a hypercube which is given by the couple PH, where P is the center of the Zonotope and H denotes the generation matrix of the Zonotope. Here, two examples of three-order Zonotope in a two-dimensional space and a three-order Zonotope in a three-dimensional space. For the proposed system, we suppose that the initial state, the state disturbance, and the measurement noise are unknown but bounded by zonotopes, where H0, HW, and HV are the generation matrices. Under this assumption, the proposed fault detection observer structure is given by this set of equations, where x hat is the estimation of x, and LQ is the observer gain to be designed. For this proposed observer, the objective is to compute the fault detection observer gains LQ that reduce the sensitivity, increase the sensitivity of the residual signal to fault using a novel pole assignment technique and reduce the effect of uncertainties using the H infinity performance. The error dynamics is split into subsystems in order to facilitate the analysis of these equations. The first subsystem is decoupled from the effect of the fault and will be used to analyze robustness against uncertainties. And this subsystem is only affected by the actuator fault and will be used to analyze fault sensitivity. We begin by the fault sensitivity conditions. So the fault detection observer gains are designed such that this condition holds. In fact, if this condition is satisfied, it can be easily shown that the residual signal depends on a scalar lambda, okay? And it is required to increase the value of lambda in order to increase the fault sensitivity of the residual signal to the fault F. Based on the following lemma, which gives the general solution of the equation AB equal to C, the fault detection observer gains can be obtained and given by this expression, where S is an arbitrary matrix to be designed. In addition to the fault sensitivity condition, the disturbance attenuation condition should be also ensured in order to provide more accurate fault detection results. In this part of my talk, the disturbance attenuation is based on H infinity performance, and the design conditions are given in terms of linear matrix inequalities. Once fault sensitivity and robustness against uncertainties are achieved, the fault detection decision is based on determining whether the residual signal is excluded from the residual zonotope or not. The residual zonotope, R, is given by the couple 0RK, where this matrix satisfies the following iteration equation. This notation represents the complexity reduction operator. In fact, when using zonotopic techniques, the reduction operation is used to constrain a high-dimensional zonotope with a lower dimensional one. And it is worth noting that more accurate fault detection results could be achieved when using higher dimensional zonotopes. So in the simulation study, a discrete time switched system with 3 subsystems is also considered. We suppose that the fault occurs after the time instance 20. And in the simulation study, we have performed a comparison between the proposed fault detection observer and a method without considering optimization tools. It means a method without considering robustness against uncertainties and without considering the novel pole assignment technique. And we can see that from this figure, the residual signals, which are in blue points, are excluded from the residual zonotopes when a fault occurs. However, when using a method without optimization, the residual signal is always included in the residual zonotopes. It means that the fault cannot be detected. So we can say that the proposed zonotope-based fault detection method provides accurate fault detection results with relaxed design condition and based on higher dimensional zonotopes. However, we should note that the additional dimensional growth of the zonotopes may cause heavier computational burden. That's why ellipsoidal analysis could be developed and could be considered as a good trade-off between fault detection accuracy and computational complexity. The ellipsoidal analysis is based on simple matrix calculations and does not require any reduction operator. In the last part of this section, we aim to propose a robust fault detection method using ellipsoidal analysis for the following discrete time switched system subject to sensor faults. We give the definition of an ellipsoid set, which is given by the couple Cx, where C is the center of the ellipsoid and X is a symmetric definite, positive definite matrix, which represents the shape and the size of the ellipsoid. We suppose that the initial state, the state disturbance, and the measurement noise are unknown but bounded by ellipsoids. And under this assumption, the proposed fault detection observer is based on the TNL structure, where the T and N are constant matrices that should be designed to satisfy this condition. It is worth noting that if TQ is equal to the identity matrix and NQ is equal to the zero matrix, the proposed fault detection observer is reduced to the commonly used Limberger form. So by introducing T and N, the proposed structure can provide more design degree of freedom. In order to facilitate the analysis of the error dynamics, it is split into subsystems, one decoupled from the effect of the fault, and the other one is only affected by the sensor fault. And based on this representation, the goal is to compute the fault detection observer gains such that the error system is stable and the residual signal satisfies the following L-infinity performance. Sufficient conditions are given in terms of linear matrix inequalities using multiple quadratic Lyapunov functions. After designing the fault detection observer gain, the residual evaluation is based on determining whether the residual signal is excluded from the residual ellipsoid or not. This ellipsoid is obtained based on the following theorem and given by the couple 0R, where R satisfies the following iteration equations. To highlight the effectiveness of the ellipsoid-based fault detection method, we consider a discrete time switched system with 3 subsystems, and we consider 2 fault scenarios. In the first fault scenario, the fault F is equal or with the amplitude equal to the 0.25, and it is supposed to occur after the time instant 14. And in the second fault scenario, we suppose that a fault with a small amplitude F equal to 0.08 is supposed to occur after the time instant 14. In the simulation results, we have performed a comparison between the proposed approach, which is based on the TNL observer, and with a Limberger observer. So we can see that in both cases, I mean, when a fault equal to 0.25 and when a fault equal to 0.08, the residual signal is excluded from the residual ellipsoids. However, when using a Limberger observer, the small fault, which is in blue points, cannot be detected and the residual signal is still included in the residual ellipsoid when using Leuenberger observer. At the end of this presentation, so interval estimation and set membership fault detection techniques are investigated and achieved. First, an interval approach is used developed where stability and non-negativity property are relaxed based on the polytopic shape of the system parameters and expressed only on the verses of each polytope. And a novel interval observer-based TNL structure is designed also for a discrete-time switched system using L-infinity performance. And based on set membership framework, Zonotopic and Ellipsoidal analysis are considered for switched systems in order to deal with fault detection. Thank you for your attention.
Thank you, Chaima. We have time now for questions. Would like to start for the questions.
Okay, maybe let me start. Chaima, many thanks for this extremely good presentation. I liked it very much. And maybe let me start with the slide number 18.
Okay.
It's one of your assumptions there is that you know the output matrix exactly, the matrix C.
Yes.
Which modifications are necessary in the case that you also have, let's say, some switch behavior in the system outputs that, for example, in different modes, you have different sensor configurations?
I think that there is no theoretical problem when using more than C. It means when using C sigma K, for example, there is no theoretical problems.
Okay, that means just your original equations, everything that you had as design criterion just remains the same, just modifying the corresponding output matrix from mode to mode.
Yes.
Okay, and maybe right away here, a second question. Your output equation doesn't depend on system inputs, but in many practical applications, you have something like a feed-through term, depending, for example, on the control term, directly the output equation. Now, if you know this influence exactly, I think it's very easy. That's what you always do, for example, in the Leuenberger design. You just subtract the influence of the input signal and that's it. But in cases where you have uncertainty in the corresponding feed-through term, for example, uncertain gains, how would you deal with such a scenario? Did anything like this come to you when dealing with your application scenarios so far or not?
In this thesis, I just focus on theoretical, maybe theoretical system, maybe in practical cases, it will be, of course, more complicated than this simple representation.
Okay. So what I assume would be a straightforward solution is just to map the influence of a feed-through term into the noise term V. That's something you could do, but I think that's definitely conservative.
Yes, maybe.
Yeah. Because from a practical point of view, if you just go to, I think it was the slide number 2 or 3, where you had the sketch of the electric circuit. Such a phenomenon directly occurs in cases where the control input, the system input is, for example, a current, and you're measuring the voltage over multiple circuit elements, for example, resistors or capacitors at once, and you try to reconstruct the system behavior from that.
It will be more complicated when
yes, definitely.
Measurement noise. Even when we suppose that the measurement noise is unknown but bounded.
Okay, yes. Then many thanks. Anyone else from the audience with a question?
Thank you.
I have one, if you have time.
Yes, time is no matter here.
Okay, just a question about the Zonotop approach. Yes, you said that to detect errors, it is required to have high dimension Zonotops. Otherwise, you are not able to detect errors. I understand that, of course, if you use high dimension Zonotops, it takes time. Do you have a theoretical result or some insight about the dimension of the Zonotop units? How vertices and so on? Are you able to bound to provide some insight about that?
Yes, I said that when using Zonotopic methods, in order to obtain more accurate fault detection results, we should constrain Zonotop with a high dimensional Zonotop. But even with a low dimensional Zonotop, we can detect the fault. So by augmenting the reduction, the operation reduction, we can achieve or we can improve the fault detection accuracy. But I don't know. It is the dilemma between the fault detection accuracy and between the computational complexity. I don't know if I can.
Oh, thank you for the answer. Okay, thank you for the answer. By the way, I understand that you decided to move to ellipsoids, and okay, so maybe it could be interesting to more investigate the Zonotop approach to clearly decide what is the performance of the approach. Okay, thank you very much.
Thank you for you.
There's some additional questions. We have time.
Hi, Chaima.
Hello.
I have a small question.
Okay.
In your observer design for LPV switch system, you use 2 pairs of TNL matrices. My question is that why do you use 2 pairs of TNL matrices?
Okay.
It seems that only a pair of TNL matrices is enough, I think.
In the augmented system?
Yes.
I will see.
You use 2 pairs yes. of N and L.
Yes. We can use 1 pair of TN, but in the augmented system, we have 2 pairs of LQ. So in the resolution, I don't know if I can explain it without not using equations, but here, for example, the matrix A, we have overline TQ, AQ minus overline LQC. So if we put, for example, 1 TQ in the resolution, it will be overline LQ. No. It is just for the resolution of the augmented system. When using 1 TQ, it will be not complicated, but it will be, we can prove a confusion between the overline LQ and underline LQ, but it is possible to use TQ, 1 TQ and 1 LQ.
Do you think you get some advantage by using 2 pairs of matrices?
Advantage, maybe it gives more design degree of freedom, but I didn't operate any simulation comparison between if using only TQ and when using overline and underline TQ. I don't know if it implicates some, it can influence the simulation results or not, but that is not what it's called.
Maybe you can have a try.
Okay, okay.
Since we are in the case of linear systems, I think that we don't have here additional degrees of freedom, I think.
Okay.
Because the matrices are the same for the two pairs. To solve the LMIs, it's the same thing. I think that we don't have here some additional degrees of freedom. But in simulation, maybe you can check at least for simulation if it is better or not.
Okay. Okay.
Okay. Thank you. Thank you, Chaima. CEDRIC.
Yes, I think a very simple check would here just to compare the outcome of those matrices if they are identical or not.
Mm-hmm.
Okay, I just seen that Naima has raised her hand. Do you have any question?
Yes, sir. Hi, Chaima.
Hi.
I would ask you some simple question.
Okay.
How did you measure the computational complexity of interval observers, Zonotopic, and ellipsoid approaches?
Okay. Well, as I mentioned in the presentation, interval methods are based on designing two bounds using simple mathematical calculation processes such as addition and subtraction operations. However, the design of interval observers requires not only the stability but also the non-negativity of the estimation error, which is a conservative assumption. On the other side, Zonotopic methods do not require the non-negativity assumption. Meanwhile, they require the reduction operation to constrain higher dimensional zonotope. And as mentioned, the additional dimensional growth may cause heavier computational burden. Compared with the Zonotopic method, the basic operations for ellipsoid techniques can be reduced to simple matrix calculation and do not require any reduction operator. So it can be considered as a good trade-off between fault detection accuracy and computational complexity.
Okay, thank you.
You're welcome.
We have time for other questions.
Okay, maybe I have a further one. What you currently did is you did only, just let me say this in quotation marks. I think that's already very interesting result. You only detect that some kind of fault has occurred. But currently you're not able to isolate which type of fault has occurred. It's more or less just a black and white answer.
Yes.
Do you have any ideas how to extend the approach in such a way that you can also perform fault isolation?
Yes, in this project, we are interested in just fault detection for switched systems. But of course, it will be interesting to isolate the fault. I saw some recent works and some works in the literature that are based on constructing a bank of observers in order to isolate the fault. Maybe it will be interesting to use this approach in order to identify if the fault comes from for example, the sensor or from the actuator.
That means you would propose to run a bank of filters in parallel or observers in parallel, something like it is done, for example, in a stochastic case when you do some multi-hypothesis Kalman filtering.
Yes.
Okay.
That's...
Other questions?
And so, what are the next steps you would like to address this bank of filters to isolate errors, or?
The next step after isolation? Maybe it will be the identification of the fault. And because the fault diagnosis can be achieved using 3 steps. The first step is the fault detection, and after that the isolation of the fault, and finally the identification of the fault.
And there is nothing to do to mix the different approaches. For example, to start with the interval-based observer, because it is something running fast. And then if you identify some errors, to use Zonotop one, high dimension Zonotops approach. I don't know if
yes.
it is something interesting.
Yes, I think it is interesting to begin with the interval method when isolating the faults. After that, maybe when using small, or when considering small a fault with smaller amplitudes, it will be interesting to use the Zonotopic approaches and compare the both techniques.
Some hybrid approach, or use a different complementary approach to speed up the computation time, and also to have precise inputs, outputs, results. I don't know.
Yes, it will be maybe interesting to use hybrid combination.
Yes, maybe one thing that I would like to add to the thing that Stefan just said. I think it's even a 4th step that exists. After you have also estimated the fault, you can even perform some reconfiguration of the control law. And I think if you have very good estimates, this would be really valuable to do in the, maybe not very near future, but in some further steps
yes,
ahead.
for sure. It is more than only detect a fault and design an observer. It is also to do the loop, the complete loop. So therefore, also to change the control law and okay, reconfigure. Okay, I understand that. Oh, interesting. Yes. Very nice presentation.
Thank you.
And clear.
Thank you.